You will have heard in the course of the morning about the need for a theoretical foundation for systems engineering. And you'll be aware of the work that has been going on over the last couple of years. There's been shared endeavor between the National Science Foundation, INCOSE, and the Systems Engineering Research Center to look at the problems that are arising because of the increase in complexity within systems engineering. And you will see these kinds of comments in the reports that are coming out that are pointing out very specifically that we don't have a theoretical foundation, so that when things go wrong, it's very difficult to make adjustments in a systematic way. And these kinds of problems have been identified and a strategy for it incorporated in the INCOSE vision. So this is specifically to address rising complexity. And when you look in the INCOSE vision, you'll see this very nice phrasing, which I'd like to draw your attention to, that says we need a system science to underpin the practice of systems engineering. And specifically, we need a common vocabulary and general principles explaining the nature of complex systems. That is a very nice framing of what it is that we are trying to achieve here. We are looking for principles that explain. So this is where the science comes in. We're not trying to figure out how things work. We're trying to find out what is the nature of systems and do it in a scientific way, which will give us the explanatory models that we need. So unfortunately today, system science is not yet where we want it to be. We do have such a topic. It's named in the literature and it's taught in universities. And it's basically composed of a very big range of systemic methodologies. So we've got systems dynamics, soft systems methodology, operational research, critical thinking and practice. There's hundreds of these things. But they're typically fairly weakly grounded in theory. We have a number of specialized scientific theories about aspects of systems, like control systems theory and hierarchy theory. But they're very specialized, and we don't really have a general theory of systems. What we have instead is about a dozen heuristic principles that you find in pretty much every book on systems architecting. Now, I and a number of others are working on developing a scientific theory that would replace these heuristic principles with scientific principles and a theory around it. So you'll be aware of the work of people like Len Troncali and Bill Schindel. There's very scientific approaches that's looking at the broad phenomenology of systems. So there's a lot of modeling and phenomenology going on there. And some of it is already becoming useful within systems engineering, like Bill Schindel's work on the S-star model. But we haven't yet figured out exactly how to develop the scientific principles that we need. And we're just starting now to make progress within this, a project in the System Science Working Group, which I will tell you about this morning. So this is just an example of the systems principles that we have today. So you find this all over the literature, and the terminology is very inconsistent. So people talk about principles, or they talk about laws, or they talk about core concepts. This is the list from the Systems Engineering Handbook, and you see the kind of thing that it is. Explains the system is something that has emergent properties, or reminds you to take note of the fact that it changes the environment, and the environment is something you have to consider when you're designing a system. So they're really aphorisms that package the accumulated wisdom of the experience of systems engineers. And it'll be the foundation of the system science which we will have one day, but it's not a system science yet. Saying that, I don't want to diminish the power of heuristics. Of course, systems engineers are aware of the fact that the heuristics are empowering them. But there's a long history of heuristics working well in terms of supporting technologies. So I'll give you some examples. So even before the scientific revolution, there was the most amazing technology that was really based on heuristics. It's careful observation with the scientific attitude of what's going on in nature, and then developing technologies out of that. So we had pretty good steel in Japan. We had, in the 12th century, colloidal copper glazes. That's not a red vase. That color comes from a diffraction grating caused by colloidal suspension of copper in the glaze. So creating something like that when you don't have chemistry and you don't have thermocouples is an amazing achievement. And of course, we had things like megalithic engineering in ancient times. That's an interesting stone. This is in Lebanon, at a place called Baalbek. And that is a stone lying in the quarry. And the Romans built that temple of Jupiter up there on the hill, sort of a mile up the hill from the quarry. And there are these big blocks of stone. That stone is 20 meters by 6 meters by 5 meters. It weighs 800 tons. And you can see them in the foundation of this temple complex there. You can see that's a human figure standing there. And there are 3 of these big blocks lying in the foundation there. We have no idea how they transported those kinds of blocks up those hills. So engineers have been amazing in ancient times, and they did it with heuristics. So heuristics are powerful, but we have a strong incentive for trying to get beyond that. So here's my example. So before the scientific revolution, of course, people had control of fire, and we had amazing technologies that was made possible. Smoke-cured meat and burning rockets and all sorts of interesting things. But when you look at the technologies that you have at that time, they all depend on basically heating or burning things. So the nature of the phenomenology that you're controlling also then determines the kinds of technologies that you're seeking to create. Once we understood the nature of fire in terms of the chemistry and electromagnetism, it transformed the technological landscape. You couldn't imagine the kinds of things that we could make once we understood this scientifically. You could imagine those kinds of applications by thinking about the nature of fire. And that is the transition that we can foresee coming in systems. That if we understood the science of systems, we will be able to design things that nobody could imagine today is possible. So, is there such a science? Well, I think there is, and my predecessors have all argued for it, although it's been pretty hard to develop. And the idea is basically this, that if you look at the history of evolution of complex systems in nature, you see a hierarchy of systems evolving over time. So nature is innovative and introducing new systems all the time, up that red line. And engineers are studying the designs that you see in nature because they're highly optimized. So a group like the Natural Systems Working Group is looking for design patterns, engineering patterns. So these are known good solutions to complex problems, which if we can model them, we can reuse them in our own engineering designs. Now what you see in nature is that those known good solutions to complex problems are recurring isomorphically across different kinds of systems, across the systems hierarchy. So speaking anthropomorphically about nature, nature keeps rediscovering the same solutions in different contexts. And that gives the idea that there are general principles at work that are being satisfied and are being employed in this kind of design process. And that is what we are trying to discover. And if we understood them, we might be able to innovate in the way that nature does and optimize in the way that nature does. There are all kinds of things happening in nature today that we really don't have a good scientific understanding of yet. And it may be that their understanding of systems will help us extend fundamental science and in that way provide an even broader basis for technology for the future. So on the right-hand side there I show the Penrose tiles. These are tiles that cover a surface area without any gaps in between. And you get a three-dimensional version of this. And they occur in nature, so they're called quasi-crystals, where the stacking structure is space-filling but is non-repeating. And you can show mathematically that there's no algorithm for predicting what is the next step in the assembly of such a structure. But nature knows how to do this kind of thing. We've got 12 kinds of quasi-crystals that have been discovered. So if we really understand how nature innovates and how nature optimizes, we'd be able to design things and manufacture things in ways that are really beyond our imagination today. So what are these principles that we are looking for? So I will briefly explain the origin of this idea from a philosophical point of view. You've all seen a picture like this. So if you have a naturalistic system, which could be either a natural system or a technological system that is subject to the laws of nature, a naturalistic system would start in a certain state and then move through a series of states through causal processes. And we can model it using formal systems. So you encode the starting state, you have a series of propositions which we infer subsequent states. And if after a while you get to a state which you decode using the same logic, if your decoded result matches the state of the natural system, then the formal system is a model of the natural system. And you can generalize that so the model becomes a theory of the natural system if it applies to the class of natural systems rather than the instance. So that's what engineers do when they model, and it's what scientists do when they study systems in nature. But what we're more interested in now is the assumptions that are behind this kind of picture. So we make general assumptions about the nature of nature, and these are assumptions about what we think have to be true in order for this modeling relationship to work. So for example, you would assume that all changes have causes or changes all produce the same effects in the same context. And you could use that then as a warrant for how you build your model and how you investigate nature. But these are really just assumptions about the nature of nature, and you can't really prove them, but you can gain confidence in them as your models become more powerful. So what do these principles do? Well, here's a quick sketch. So what we have is that scientists really model nature as we find it, what we call manifest nature. And that science then enables systems practice and engineering. And through practice and engineering, we can intervene in manifest nature. Now, manifest nature occurs because of the conditions set up by the nature of nature, and that is really what is being captured by those general assumptions about the nature of the world. So the metaphysics of science is really the discipline that is trying to uncover these assumptions that we make and make them explicit, and in that way build up our understanding of the nature of nature so that we can empower our theoretical understanding of manifest nature. Now we can transcribe this kind of idea directly into the system situation. So we think that if there is such a real thing as a systems concept, that it has relevance for the study of nature and that there could be a system science, then it will proceed in just the way that science does in general. So we can say that system science will model manifest systems. System science will enable systems engineering and practice, which allows for intervention. And systems philosophy will help us uncover the nature of systems. So you see the linkage here with the ambition that was in the INCOSE vision, where it said we're looking for general principles that explain the nature of complex systems. We're looking for this piece that is down there. So I will show briefly how these kinds of principles would empower our work going forward. So you see here, this is a model called the Principles, Laws, Theories model of modern science. And it explains how principles work in developing science and eventually engineering. So what we have is you have worldviews which have got a whole bunch of assumptions in them, some of which are your assumptions about the nature of nature. And from those you can distill the principles as I've shown before. And then when you've got principles such as all change is proportionate to change elsewhere, you can apply them to your observations. You wiggle something and see what else wiggles proportionately, express that as a relationship, and in that way you discover laws of nature. Once you understand your laws of nature, you apply them to your observations, and you can make theories about it. So if you've extracted a law such as Boyle's law, which expresses very nicely the relationship of one thing to proportionate change somewhere else, or Newton's law, you can apply them to observations. So you've got Newton's laws of gravitation, you can apply to astronomical observations, and you can predict the next eclipse or the next tide or the return of a meteor. So those theories would then allow you to make predictions and explanations. And we check those theories using things called theoretical virtues, which is another part of philosophy of science. So there's a long list of theoretical virtues. You'll be familiar with ones like falsifiability and Occam's razor, which says to simplify your theories. But there's a list of about 25 of these things in philosophy of science that looks at predictive power, explanatory power, consistency with theories we already have confidence in, ability to generate new technologies, and so on. So you check your theories against the theoretical virtues. If they work well, then good, but if they don't, you go back and you improve your theories. If you still can't make a virtuous theory, you go back and you think maybe the laws are inadequate. Maybe you need extra terms in them, maybe you need extra laws. So your research focus is there. If you then make better theories, then good, but if you can't, you go back and you worry about your principles. If you still can't improve, then you go back to your worldview and you say, well, where do my general assumptions come from? So in your worldview, you always try and balance between your knowledge, your intuitions, and your experiences. So maybe the way in which we do that in order to set up the assumptions that we're going to work with needs some attention. So eventually you will get evolution of worldviews from this. So the interesting thing that you see from here is that all of this evolution of theories, laws, principles, and worldviews is driven by the theoretical virtues. That's the sharp end of this whole process, and everybody focuses on that. And if we pay attention to that, we can improve all of this going back all the way to worldviews. So the change can be radical, but be aware that the change does not come from having a lively debate over here or a lively debate over here. The debate is driven here through theoretical virtues. So we've been looking at how we can improve this. So we have a project that James referred to earlier, our joint project between the System Science Working Group and the ISSS. And we've been, have I skipped a slide, I think, somewhere. So we've been looking at strategies for developing scientific systems principles. And here's the first one. So we looked at that picture that I showed before and made the correlation between the general picture in science and the picture that we have in systems science. So we say scientific principles are our most general assumptions about the nature of the world. Then scientific systems principles would be our most general assumptions about the systemic nature of the world. So if we look into that, it suggests that if we take something like the heuristic principles that we have, or something like the science concepts that we have, the systems concepts that we have, and the systems heuristics that we have, and we apply our ordinary scientific ideas to it, we might be able to derive scientific systems principles and scientific systems concepts. So we've been working on this project for about 2 years now. So first we'd spent a lot of time clearing up the conceptual terrain. I'm sorry, a slide seems to have disappeared from the deck, which explained the outcome of the project. Oh, was it way back there? Don't think so. Yes. Oh, there was that one. Did I skip over that too quickly? So this is the nature of the. Thank you. This is the nature of the project that we've been having within the System Science Working Group. And the first step was to try and clear up the conceptual terrain, which is what I showed you the results of when I was talking about the nature of systems and systems principles. So we've done a lot of work through webinars and workshops and published a range of papers. And we've been disseminating this work in recent times. So a week ago, we were at the NSF. We had a poster there about the work, and it's in the hallway just next to the registration desk if you want to have a look at that. And we've got the full-day workshop on Monday. And there'll be a paper on this coming up at CSER. So that's all the clearing out that we've done in the project. And that was the first project that we then undertook. We have identified 6 strategies for identifying scientific systems principles through this work that we've been doing. So we did a pilot on the first one. And we were able to derive 3 scientific principles. So I'm not going to explain how they work here. But I'll mention what they are so you can see the kind of direction that this is taking. And I'll be explaining this in some detail on Monday in the workshop that we have in the System Science Working Group. But we have 3 scientific principles. I'll just state them here in a kind of qualitative way. But the way in which it is framed allows us to now express these things in terms of exact scientific concepts. So we have one which we call conservation of properties, which is our kind of system version of conservation of energy. And it gives us already new strategies for research and analysis. We have principle of universal interdependence, which gives us a scientific way of talking about holistic perspectives. And it identifies new kinds of leverage points for us. And then the principle of complexity buffering, which helps us to optimize across leverage points. Now, when you look at these principles, as I'll explain on Monday, the ideas behind them are not actually that new. Many of them have been within our community for a very long time as heuristic principles. But what we have found is a way to connect this kind of thinking about systems with foundational thinking in science and start expressing these ideas in exact scientific terms so that you can formalize it and then incorporate them into a formal scientific theory. So we have a number of next steps coming up. Our workshop, which we've already mentioned. We have 5 other strategies which we want to try out and see if we can develop some further principles. And this whole network of principles that we are defining will, of course, have to carry on being refined over time. And once we have some principles, we will be able to start discovering systems laws. As you'll see, we'll remember from the PLT model gives you that idea. And, of course, then we want to integrate these principles and laws into a foundational theory of systems. And from that, develop methodologies which we would be able then to use in systems engineering. So, of course, this is what we're trying to get to a point where we can scientifically predict the outcome of design decisions, even at high levels of complexity. This is what we're really starting to struggle with now in systems engineering, that we don't have a basis against which to check unexpected behavior. And what we really want is to be able to explain, design for, and control emergence in complex systems, and then innovate and optimize in the way that nature does and make systems that are resilient and robust and supportable in the way that nature illustrates is possible. And from this, we think we will get novel technologies. And in the same way as I showed earlier, the transition from heuristics-based technology to science-based technology, I think the future of systems engineering will look radically different once we have this theory. Thank you very much. We have, I hope, a few minutes, yes, 5 minutes left over, so I'd be happy to take some questions.